some reason, these are set up to return the most dangerous thing possible when they're used incorrectly, and we have to sort of prevent that from happening.
This architecture is very harmful.
Well, I mean, look, the other way of looking at it is JavaScript was designed to report as few errors as possible, because if you write a web application, your users are someplace else on the web, and they don't really want to see your error messages. They want to see kind of best effort execution of your application.
Will you replace these with useful things that are almost the same as sort?
Yeah, I'll tell you how to do it. So first, this is 3 steps. One is,
Just not let people sort.
yeah. So first step is, let's get some sort of workspace. Let's figure out how to separate the namespace of an untrusted application from our own, so we can write these functions and prevent access to global things. Second is get some control over access to scope. And the third will be take some built-in things and redefine them so that they only do good stuff. Okay, so second phase is with this prevention and this runtime testing, then not only do we prevent programs from accessing the protected global things and names, things with the same name, and we get access to the global scope. So this is useful. And then we have another variation on it where we just change the runtime test so that it also tests whether it's a local scope, and we can prevent access to that. So that's a very minor modification. So at this point, we know how to control what global things are accessed and how untrusted code gets access to the scope. And then, as you asked, I couldn't have planted a better question. We redefine some built-in things so that they're safer to use. And that way, you don't prevent good code from executing. You just prevent bad executions from occurring by runtime tests. So this general mechanism, we've still prevented in the version we've used in our theorems and proofs. These 2 functions. Eval function is a kind of version of string evaluation that produces the text of a compiled function that then can be called later. Constructor is a kind of roundabout way of getting at function. So there are these 3 things that are not in the language that we've actually proved things about. But we could also apply this same kind of trick and allow good uses of these things in various ways. So basically, what I wanted to summarize here in this part of the talk is a mathematical method for modeling the way programs execute, and a set of theorems about variants of subsets of JavaScript that tell you that programs written in this subset of JavaScript do not have certain dangerous kinds of behavior that would pose a threat to Facebook, advertising publishers, the other kinds of iGoogle pages, mashups, the other kind of examples I gave before. So now let me say a little bit about comparisons with what Facebook and AdSafe and these other companies have done. So the Facebook mechanisms are pretty much along the lines of the things we've described. One of the things that Facebook does initially with an untrusted application is rename all the variables. And so really the tests that we're applying are things that are applied after this variable renaming. But the fact that variable renaming preserves the execution of the program, if you wanted to prove that, which we have, is that's dependent on it following into the subset where you don't create new variable names by string operations and so on. And they have some runtime tests. So we basically followed their pattern and worked through this from the beginning. And as we proceeded, we sent them emails saying, hey, here's a bug. Hey, here's an attack. What we did for each bug or attack we found was build our own Facebook application, upload it, and send them a link and saying, hey, have fun, click on this, see what happens. And I mean, we have good relations. Actually, it turns out that most of the Facebook employees are current Stanford undergraduates. So every class I've taught for the last couple of years has a group of Facebook employees in the back. and they're generally good students. But I mean, it's a little bit unfair. I have a really good graduate student here, and it's not surprising he found stuff those other people overlooked. Plus, I obviously really want to make the point that it's the method that we're applying that let us found a number of bugs. After their bug fixes, then they come up, we're kind of at the same point. Now, although I want to show you this one attack, just because you can't really give a good security talk without an attack. Nobody really respects you the next day. So here's our application. There are a couple different versions for some browser-related reasons. This is an attack that took advantage of their twice evaluate the argument being tested, as opposed to our once evaluate check. And then allowed to, this is now a page that's a pop-up that's executed in the global scope of the hosting page. So this is a proof that we're able to take control of the page, read any data on it, and so on. So to be fair, and as they asked me to say, you know, the Facebook team has really been great, actually. Everything we've pointed out to them, they've fixed very quickly. They've been very responsive, and it's been a pleasure to work with them. I want to say a little bit about Yahoo and the ads filtering problem. And the main point here is this is just a harder problem than the Facebook problem. And the main issue is Facebook or a social network site or an iGoogle page, anything like that that's serving untrusted content in its own page, at least knows what the larger page is that's hosting the potentially malicious untrusted code. In the advertising situation, the advertisement is going from the advertiser to the ad network, and I sort of changed the color to indicate it might be filtered in some way. Then that goes on to, I don't know what, the trout fishing in Montana page, and then this gets displayed in somebody's browser. But the limitation here for the ad network is the ad network doesn't know what's going in to this page that contains the advertisement. And that's just a fundamental limitation. It's not Yahoo's fault. It's just the way advertising works on the web. But that makes it much harder to develop a good solution for filtering this ad to make sure that in no context will it do something malicious to the end user. So the basic problem here, and this is one of the things we pointed out to ad safe people, and they added kind of a, our system is good as long as this doesn't happen, sort of qualifier, is that there are standard libraries. We looked at prototype.js as one example, that make it possible to access the eval function through new names that are not part of standard JavaScript. So if you filter advertisements based on the standard way that JavaScript gets executed, you think it's fine. But if the trout fishing in Montana site or whatever it is showing the ad is written using one of the standard JavaScript libraries, then the malicious advertisement can use things defined in that standard library to circumvent all of the protection mechanisms. So what the good people of Yahoo did after we pointed this out to them was add this sentence saying, you know, our mechanism is good as long as people don't do something bad. And here's just a kind of a picture of that. So I'm being a little bit sarcastic about it, but I think there's almost nothing they can do other than provide a tool for the check their site themselves. It's just a harder problem than the Facebook problem. So far so good. I've described working about over about a year and a half, about 4 published papers, and a series of efforts to make our proofs more comprehensive, to go from just filtering things to filtering and rewriting and wrapping global things and so on. And I think we actually felt like we're sort of done with this problem until, again, the process of writing up the final paper and explaining how we'd solved all the problems, I realized there was one thing we hadn't quite addressed very